Bruce, young fellow from Kamloops initially, how did you end up in Chalk River? Where did you go for your graduate work and how did you end up here?
I went to high school in Kamloops. I went to primary school when I lived on a farm out in north of Kamloops, and there were 8 or 9 students in the school. And I remember one thing, the school burned down. I think it was the last day of school, grade 3. And I remember that they built a new school during the summer, and we had that available, I think, about October for us 8 or 9 kids. And I can't see that happening today. Anyway, so I went to high school in Kamloops, and I remember one incident. I was working after school, sweeping out, assisting the janitor. And I remember they had a after-school lecture by Gordon Shrum, a professor from UBC. And I remember him saying that if your grades if you're within 2% of the top of the class, we need you. And that was, I think, grade 11. And I realized that I might have a chance of getting to university. So just that
Right.
spurred me on a little bit. And so we had to do grade 13 in those days. And then I got a scholarship to go to UBC. And I went down and got myself a place to stay and registered. And then I got a telegram from Queens, and they said there was an fellowship scholarship available, a provincial scholarship, one for each of the provinces, sort of. And the one for BC, the original awardee, if you like, turned it down, and it was available. So I'd never been east of the Rockies, so I said I'd come, and I packed up my goods and moved. I remember phoning up and telling the registrar that I was not going to stay there, and got on the train and got back home, and then set off again from Kamloops, and took 4.5 days on the train to get to Kingston. So that's how I got to Queens. And I did engineering physics degree. And finished that in 1951. Then I had a chance to go and work at NRC in Ottawa for the summer. And what I remember about that was we were looking at photographic emulsions that had been flown at 100,000 feet in a balloon package. So we got some of the primary incoming cosmic rays. So the idea was you looked at these emulsions through a microscope for looking for interesting things. So you scanned away and you noted down things, and about a week or two into it, I discovered a very interesting event, and I managed to spend almost the rest of the summer making measurements on that exactly through the microscope. And I'd been involved in gliding at Queen's. They had a gliding club, and some of the veterans were expert pilots. And then that summer, I went out to the Gatineau Gliding Club, which was around southeast of Kamloops, or southeast of Ottawa. What about? And then I went back to Queen's and did a master's in nuclear physics under J.A. Gray, old professor there. And they just had gotten their synchrotron going, a 70 MeV synchrotron, which they purchased from General Electric. I was making them. And I did some experiments using photographic emulsions, looking for events. Wasn't really very successful, but it was an incident I remember. Some guys from Chalk River came down, and they were going to do an irradiation in the beam, and they had a big chunk of graphite, about 3 feet long and a foot square. And the idea was they would put that in the beam, and they would filter out all the low energy events and just get the high energy events through. And one of the guys I remember, I was just a student there. I didn't really know any of them, but one was very outspoken. And later years, when I got Chalk River, that was, I realized that that was,
We'll get it afterwards, yeah. Actually, the interesting thing is that size of graphite block is almost identical to the ones that were from ZEEP, and it may have been a ZEEP block, and the museum actually has 3 of the blocks here on exhibit.
Yeah. Well, it was that. It was a ZEEP block, yeah, I'm sure. Anyway, and I remember even in my limited knowledge then, I realized that was not the right thing to do if you wanted to see the high energies, because the high energies get attenuated maybe faster than the low energies even. So I did all my irradiations without any graphite filters.
Right.
Anyway, after that summer, I got a NASA fellowship, and this took me to University of Liverpool, where I worked with names. Anyway, I did 2 years there, doing nuclear physics, work on the Cockcroft-Walton accelerator. And I learned a lot of Joe Almquist was there at the same time.
Uh-huh.
He No, he was there for the first year. No, we pretty well completely overlapped. He'd been at Chalk River for some time and had taken time to go and get his degree at Liverpool. But he had the background in all the problems with leak detecting and the things that you have to do to keep an accelerator going. So I learned a lot of physics from Joe. And I finished that. I was lucky I got my degree in 2 years there, and then came to Chalk River in 1954.
In 54, okay.
Yeah.
And then over the next few years, I did a little bit of digging into the literature, and I think from then to about 1964, you were involved in a lot of things with a lot of illustrious early people like Bob Hart, Alec Eastwood, Ralph Green, Bruce Gidley.
Yeah.
I think I counted 30 AECL reports during that period. Mostly, I guess, on looking at thermal cross sections and things of that manner, both at NRX and NRU.
Yes, we didn't use NRU very much, or NRX, NRU very much. But when I got there, Jeff Hanna and Phil Tunnicliffe had an idea for trying to measure the burn-up of U-235 in NRX. They were producing plutonium for the U.S. at that time. Anyway, they had an idea for doing this with a counting gear because the mass spectrometer people were having trouble getting the accuracy they thought they needed. So my first experiment was one that they had thought up, and we set up a beam line from NRX. Bert Brockhouse and company were using all the normal beam lines, so we had a special one from one of the what's called self-serve holes, which weren't used very much. So we had this set up, and Jeff Hanna made some electronics, and we set up a back-to-back ion chamber, pair of ion chambers for comparing the fission rates on two sides and the alpha rates on two sides. And the idea that they had was that when you're doing this, if you're looking at just natural uranium alpha rates, they're very slow. And you can get the U-235 from the fission rates quite easily in a beam like that. But so they thought they could boost the alpha rates from U-238 by irradiating the samples and building up some plutonium-239, which would be proportional to the U-238 content and had a much higher alpha rate. So we got all set up to do this, and I remember we got the first samples back that were irradiated in little capsules about this big, sealed by actually fusing the top on. Anyway, when we got it out and we opened it, and I started looking at the alpha activities and so on, I found the whole thing was full of alpha activities. And I had a problem. I had to try and figure out what that was from. And the ion chamber resolution we had was not quite, not very good. Anyway, I finally found out that this alpha activity was polonium, and it turned out in the machine shop where they'd machined some of the little pieces, spacers and so on, to hold the samples in place in this capsule, they'd been machining some bismuth pieces sometime in the past. It wasn't right immediate. And so there was enough bismuth contamination on those pieces to
Give you the
give you
polonium.
give you the polonium.
Yes.
Anyway, so that really, if you thought about it, then the method of measuring that way was very subject to contamination, and you really didn't look like a good way to go. And in the meantime, the mass spectrometer guys, I can't remember his name, had got their machine going, and were making measurements at all
Was
the
it
measurements they
Lounsbury,
needed.
maybe?
Lounsbury.
Lounsbury, yeah.
Yeah, Lounsbury. And so he was able to do things accurately enough, so we gave up on that. And
When you first started with that column, you had to do some characterization. You gave us a few years ago a donation of a notebook that Brockhouse had
yeah.
he had made some early measurements. Was that part of what was needed to characterize the beam?
yes, but those were his beams on
Yes.
that he was using.
Yes. But it's nice for the society to have something
Yeah.
in Brockhouse's handwriting in the collection here.
Well, I remember trying some of the filters just to see what I could make of it. But anyway, that was my first effort. It was an interesting event. With that the beam stop had a big tank of aluminum tank of jelly, boron-loaded jelly, to absorb the neutrons, thermal neutrons that will thermalize and absorb all the neutrons. And you notice one day that the tank was swelling, kind of just distorted a bit. It turned out that the boron-loaded jelly was contaminated with some greeblies who grew, and were living off the jelly, and they produced a gas, and I know that gas was now CO2, because they were essentially doing what we do. We
Digested?
burn our sugars with CO2 and produce CO2. Anyway, we had to open the tank up, and the reason for using jelly was that it was less mobile than water. So if we don't want boron anywhere around the reactor.
Right.
And anyway.
Was this an edible food jelly that was used, or?
Yeah, I think so. I don't remember
For sure.
exactly, but
Yes.
and so we put some antiseptic stuff in, closed it up, and it was all right.
Well, there were a lot of experiments during that period that you were certainly involved on.
Yeah, well, after that, I had all this gear sitting there, and I had the chemists could produce samples that were needed, and so instead of doing that experiment, I used the equipment to measure the cross sections for fission in uranium 235, 233, plutonium 239, plutonium 241, I think. Measured, we did a set of measurements to correlate the different levels, and the absolute measurements depended on what was known for the half-lives of the different alpha emitters that they used to measure the amount of material from the alpha emission, and then you could correlate that with the fission rate in this chamber, so you could count the alphas and then turn the neutron beam on and count the fissions and compare and measure the ratio. Yeah.
A lot of that was crucial data even for characterizing fuel that eventually went into CANDU. I mean, you needed all of these cross sections and information, so that was key early information on fuels.
Yeah. Well, yeah. We continued that in using ZEEP. I remember measuring in the ZEEP rods themselves, which were metal rods about that big. We could measure the relative cross sections and the distributions of the neutrons getting absorbed in the rod and out in the water. We did a lot of measurements on that at room temperatures, but then at that time in the reactor designs, they had pretty good knowledge of things at room temperature from lattice measurements in ZEEP, but they had very little information on how these varied with the temperature of the moderator and the coolant in these assemblies. So we set up a pressure tube, like in the CANDU reactors, a pressure tube with fuel bundles in it, and special bundles that we could take apart and put detectors in and so on, and then run this up. And Russ Turner was the guy. He set up the. He had a huge pump that was sitting around from something, and if you ran that pump, it warmed things up rather rapidly. So he set that up so we could circulate coolant through the assembly. So I remember we set up we take the top off, or move it back, shielding back on top of ZEEP. We'd pull out the top part of the bundles and put our foils in, and there were, I think we were doing 19 element bundles, and put it back together again, put the top on, and you'd start up the pump and it would warm it up to the temperature. We went up as high as pretty close to 300 degrees.
Wow.
and and the pressure, of course, was. I remember wondering about the pressure, about the what was happening at the bottom end of the pressure tube. Knew the pressure tube was all right. Top end was all strong, but the bottom end had a screwed-on cap, and we wonder if that came off, it would blow coolant into the bottom, would raise the level of the moderator, and
Right.
and you have a neutron excursion. Anyway, it all worked. I remember we must have worked for about a year or two on that. Bruce Chidley was one. It was, and a lot of help with the technical guys, which I can't remember the names anymore.
You know, Parker Alfred was one of the
Yeah,
people into there. Yes.
yeah. So we did a whole set of things. The normal heavy water coolant, and we did light water coolant, and mixtures, and even did air coolant. To see just how all this went. And I don't know how much ever got used by the guys doing the calculations.
There's a lot of basic important data, though,
Yeah,
was acquired there. I have to make full disclosure, and that is to say that in 1965 I came for a break in my graduate work, and you were my supervisor at that time,
Yeah.
and we did an experiment in NRU in that 3 months I was here.
yeah,
And then you and your family had a sabbatical and you went to Argentina.
yeah.
Eventually, we did get CANDOs into Argentina, but what was the status of nuclear research and things in Argentina in 1965?
Well, when we'd had a visitor. No, that was the time. At that time, we used just got lithium drifted germanium
Oh, yes.
detectors, and that made a big difference in what you could do. The resolution was so good you could pick out activities very easily. So I got a hold of one of the first ones they were making in the general physics group, and it made really all the difference in some things. I remember there was one what we thought was what we call a Friday afternoon experiment. We it was Bill Walker, and who was did all the calculations in fission products, and Al Okazaki was running the I think it was Z2 at that time, but I think it was Z2. It was, and I got this detector, and I could see we could see the gamma ray line from amongst all the other grubble,
Right.
from the ion that causes poisoning out of the reactors, the one that grows in from a fission product.
The argon one?
No, Anyway, if you shut down a high power reactor, then it poisons out.
Right.
And the question was how much of this poison came from the cursor fission product and how much was produced first in the fuel, directly in the fuel. So we thought, well, we can measure that. All we have to do is make a short irradiation, and we'll look at the activity, and you can extrapolate back to zero and see how much was there in the before it started coming from the precursor, a normal precursor. Anyway, we thought, well, that's just a Friday afternoon experiment. We'll do it. I think it was 3 years before we finally got the published paper. Anyway, it just turned out there were a lot of little corrections you had to look into. Anyway, having those lithium drifted germanium detectors made opened quite a wide field of possible studies
for many people.
And we had a visitor from Argentina, and they sort of asked about things, and eventually I got it was an IAEA finance trip to Argentina. And they have a very small group there, but they had this small reactor which they had set up in the 50s. And it was still going, like 10 kilowatts. It was a neutron source, and so we did some experiments using the. They were able to buy a detector from the outfit in Montreal that was making a few of them, and they got that set up, and so we did some experiments on measuring fission products and capture cross sections and things. But that was an interesting year for us because we were able to travel around quite freely. I bought a little car, and we traveled to Chile and as far north in Argentina, right to the border. And there are a couple of episodes involved there. We wanted to go up to the Christ in the Andes, the statue up on the top. So we went up, and you go switchbacks going up like this, and the altitude up there is about 12 or 13,000 feet. So the little car had a real problem. If I could keep going, it was all right. But if I got too slow behind a bus that was going up, I couldn't get started again on a slope. So back down to the switchback below, and there'd be a place where you could back up like
run
this,
off.
Get a run at. We got up the top, and I thought, well, we'll just go down to Chile. But just over the brow, I looked down, and there was snow across. The road wasn't open. And I had to get back up on top. I unloaded all the people, and I managed to turn around and get back up on the top. And we had another good luck. We drove up to top north end of Argentina, Humahuaca. And when we were leaving, coming back, the car gave up, and I deduced that we were the coil had failed. So I got a hitchhike back into Humahuaca, went to the service station. And it was a new station, I guess, and there were shelves, and mostly bare, and there was a coil sitting there. So I bought it and turned back, and it worked. Car worked fine after that.
When you got back in 65, 66 to Chalk River, the excitement in Chalk River was really on ING, the intense neutron generator. Just as a background, the idea was a 1 GeV proton accelerator with a powerful beam of 65 megawatts. And every proton that would hit something like lead or bismuth would produce 40 to 50 neutrons. And that was the big new replacement maybe for, or future, for Chalk River as a neutron source. What did you get involved in when you got back? I think I've read that maybe up to 40% of the research people at Chalk River were working on ING.
Mm-hmm. Yeah, well, I got involved in the RF radio frequency systems for powering these high power accelerators, high power LINAC. So I was having to learn about high power electronics, and I remember we had a couple of guys, Les Burney and Riley Bird, who had worked on I think a dew line somewhere, the big radar stations up north. So they had something and some knowledge about it. And Cliff Brown and Jack Hitchcock were also acquainted with the thing. So I had to learn all, learn about that, and we bought some amplitron, it was called, and it's a modification of a magnetron, sort of, in which it was an amplifier, supposedly, instead of a free oscillator. So you could control it by controlling the input. So if you had a lot of LINAC
Right.
things, you could control the power you're putting into, like you can do with a klystron, which is the alternative. So we had, I think, two of these, and Cliff, I remember, was in setting up big high-powered power supplies to operate these, and I was involved with doing some of the experiments, and so I'm trying to understand how they worked. And then another thing, by that time, project was canceled.
That's right. So in 1968, the project got canceled, but you and Harvey Schneider got looking at using magnetrons for industrial heating, possibly drying wood, things of that manner?
Yeah, continued using the equipment for a while, trying essentially to apply the accelerator cavity techniques to making a high power magnetron. I got one to work. I tried various things. I got one to work that had about 80% efficiency, which was reasonable for the. I guess I got close to 100 kilowatts out of it, but anyway, that didn't seem to be very. Didn't go very far because you couldn't see any real applications. There were possibilities drying wood and drying hay for the guys in Peach River were selling hay to Japan and they needed to dry it. But this didn't happen often enough to support any big projects.
And
So that sort of withered out. I think now there are some applications that are going on
right.
with sort of 100 kilowatt magnetrons.
Right. Later on within the accelerator physics branch, Mark DeYoung and Fred Adams were involved into some for using RF heating that way for drying epoxies, etc., into big wooden beams and
I remember
that kind of work. Okay, about then, the nuclear physics people were getting a little bit antsy that they needed some higher energies to do continuing work. They were getting to the end of what they could do with the big tandem, so they wanted to do an energy booster. And then you got very heavily involved into that again with Harvey Schneider, and the cyclotron eventually came out of that. Could you tell us a little bit more about the thinking at the beginning of that?
Well, I just remember one day Harvey had gone to a magnet conference where they talked about some of the big superconducting magnet projects. There were a couple of rings set up for cloud chamber, big cloud chamber they wanted a magnetic field they could see the curved paths of things. So we were looking at these sort of applications, and I remember one day doing a little arithmetic on what would be needed for a booster, and I came out to the possibility that we could make something
reasonable size,
not very big, and went into Harvey and showed him the what I'd been doing, and he thought about it, and we thought about it, and at that time the French in France were making their Ganil project, and they were building normal cyclotrons to do it. They had a pair they were doing, and they were as big as a house, huge things. And we came out with something much smaller. Your model you have is Harvey's thinking on how to make iron-free cyclotron, and tucked in the center of that model is the RF model that I first envisaged for such a thing. It turned out that it's much better to use a large iron poles and sheeting, because we thought, well, if you have the coils, then you have to put some shielding around, and in order to shield those coils, you'd need so much steel that it was much more than you needed by making a normal sort of iron structure cyclotron, and there are other reasons too. But anyway, eventually we came up, and in that machine there were quite a number of innovations that we made.
Yes, in fact, the one about having control rods in to be able to shape the field always seems to be a carryover from Can-Do's, where we've got control rods to flatten the flux in the calandria.
The design we ended up with was a superconducting magnet and the iron around it, and it had shape poles for focusing, and then you have to fit an accelerator structure into it. And they wanted a very wide range of ions, from 3 MeV per nucleon, and uranium ions at 10 MeV per nucleon, and higher ones in between. But anyway, to cover the range required in the RF accelerating structure, meant most of these the machines that were built like this had to have tuners that stuck up 2 or 3 meters above the outside of the structure to get the frequency range they wanted on the resonators. So I've thought that, well, if we make a structure, a 2-element structure, it will have 2 resonant modes. One in which the if you like, the elements go in phase or they go out of phase, and if we make a 4-element thing, we could go with a what do you I guess both together or in opposition, and we could get accelerating fields for a wider range of frequencies by using both of those modes. And so we had one tuner at the top, one tuner at the bottom like this, and 2 Ds coming out. I got a little picture. This is the final 10th scale model that I used to calculate everything I needed for the final structure.
Right.
And the expert guys said you'll never get it to work if you have axial fields. This has axial fields in places. But I thought, well, if you reverse them equally, those axial fields are not going to cause any trouble, and they didn't. Anyway, that was one innovation that we had and the trim rods, of course. The alternative to that was to fit coils on the face of the poles. You could vary the current and vary the magnetic field. But with the high fields that we were using, you needed quite large currents to get the variations you wanted. So by using essentially the power of the iron on the fields, we could get the variations that were needed. But it turned out that it was a real problem to get the accuracy on the settings because they were too strong. So it's John Ormond who really worked on getting the driving mechanisms for adjusting these.
Yes, it was very, very complex. We have some photos of just how crowded that was at the bottom and top to be able to get it fitted in.
Yeah. But I guess they worked all right.
In the end, it was a success, and there were a wide range of beams extracted. There was also a medical version that you and Harvey worked on.
Oh yeah, well, when we were dreaming about things, we dreamed that you could use, perhaps make a 25 or 30 MeV cyclotron small enough that you could mount it on a gantry and you could use it as a neutron source for neutron therapy, because you could mount it on a thing and rotate it around to point the beam in the directions you wanted and so on.
Right.
And there was one of these built in Michigan that what was Blosser was leading cyclotron business there, and his sons made one of these machines too. And I think it treated people. I don't know if it's still going. Anyway, that's as far as we got on it. And of course, when they shut down Task, well, I'd done a little bit of consulting with the proton therapy machine they were building in Boston, and I could see that Task had everything you needed for proton therapy set up, because you had the cyclotron, you had the huge rooms to put any gantry equipment.
Yes.
The idea was you could bring a new proton beam around, bend it up like this, and then around and down, and then you could rotate the whole thing around and get beam where you want it. And anyway, I figured that when they shut down the Task facility, they had something that was worth probably $40 million in that time. Not much now, but and we did try. I tried to figure the best I could do was try to tell the cancer people that there was this possibility if they could do it. And we did. And Doug Milton and I went once to Toronto and spoke to the people there, but they turned it down. turn down any possibility of doing. It would require some modifications to the cyclotron, of course, which would to get 200 and we wanted 250 MeV protons to.
Direct treatment with the proton beam.
Yeah.
Yes.
Yeah.
Yeah.
Yeah. So now, in the U.S., there's an outfit called Mevion Medical Systems. They're making superconducting cyclotrons, and they're using the mounting on a gantry to rotate the beam around. And there must be at least a half a dozen of them operating now that I know of. I haven't tried to search it out.
The superconducting cyclotron was built separately from the task facility and then moved over and eventually put into operation. They successfully extracted beams from it for quite some time, and then unfortunately in 1992 the government brought in some significant cuts in the budget of Chalk River, and you took a retirement a little bit earlier than you had hoped to.
Well, actually, actually I could. I remember they were going to shut down the branch anyway. You know about all that. I remember that we got an offer, and when I went to accept it, they'd run out of money. So I remember Tom Alexander was so fed up that he retired anyway. But I figured I'm doing all right. I can I can last. I didn't really want to quit, and so I stayed a year, and then they reworked the handouts, and there were four of us: Bruce Chidley,
John Hulbert.
John Hulbert, and John Armagh.
Yep.
That's four.
Yep.
Yeah, we got reasonable handouts.
About 1980, we came back from a conference in Europe and discovered that the entire world was jumping onto synchrotrons that, as light sources that we really hadn't heard very much about. And when we had a seminar at the branch in Chalk River, and then you and Nizar Ibrahim and
Clarence
Hoffman ended up doing a study, and eventually that led to the formation of the Institute of Synchrotron Radiation.
Yeah, we formed an institute. Yeah, I guess it eventually did too. It did, yeah. I tried to do a little bit of consulting, but at the stage of looking for money, I was hopeless. I could comment on the technology a bit, but...
And the initial interest that we sort of generated from here, we had a big workshop, and it was the University of Western Ontario that was initially looking as a possible source of or home for a synchrotron, but eventually the fact that Saskatoon already had an accelerator there really led to what has been an extremely successful experiment.
Yeah, well, it's going. They have problems. They have a synchrotron, a superconducting element that gave them troubles, I remember. But it's been very successful, I think.
We should mention that Mark DeYoung, who
Mark
used to be
DeYoung,
in the
yeah.
accelerator physics branch here, went to become really the head of the mechanical setup of all of that network there.
He looked after building the machine. Yeah.
So after that, you've now been doing 30 years of gardening, and among other things, and probably the biggest winner at all the gardening shows around town, etc. Do you see gardening as a good activity for people after they've retired from work?
Oh, I think so. I think so.
Well, thank you very much, Bruce, for passing on a lot of thoughts and information from the past. 54 is 65 or 66 years in Deep River, and thank you very much for joining our series, and we look forward for more years of gardening from you.